What is an LDR? Light-dependent resistor. Have you ever noticed how streetlights magically turn on at dusk, or how solar garden lights just know when it's dark outside? Like, who told them it was nighttime? Well, the secret behind this clever behavior lies in a small but fascinating component called the LDR, or light-dependent resistor. In today's deep dive, we're going to unpack everything about LDRs. What they are, how they work, the science behind them, how to use them in real-world circuits, and where they show up in everyday life. Whether you're a beginner in electronics or just curious about how tech senses light, this video is for you. So grab your favorite drink, sit back, and let's shed some light on LDRs. What is an LDR? Let's start with the basics. An LDR, also known as a photoresistor, is a light-sensitive resistor. And here's the magic. Its resistance changes depending on how much light is hitting it. So when it's dark, the resistance is very high. We're talking mega ohms, like millions of ohms. But as the environment gets brighter, the resistance drops, sometimes down to just a few hundred ohms. It's like, the more light you shine on it, the easier it lets electricity flow through. Think of it as a light-controlled gate. When it's dark, the gate is closed. When it's bright, the gate swings open. And that's why they're called light-dependent resistors. Makes sense, right? How does an LDR work? So, how does this thing actually work? What's going on inside? LDRs are made from semiconducting materials, usually cadmium sulfide or CDS. These materials have a really cool property. When light hits them, specifically photons, those photons energize the electrons in the material. Boom! Suddenly, those electrons have enough energy to jump into the conduction band, which means they can now move freely and carry electric current, so more light equals more energized electrons, which equals lower resistance and more current flow. It's all thanks to something called the photoconductive effect, where light literally boosts conductivity. But here's something to note. LDRs are not fast responders. They take a few milliseconds, or even seconds, to react to light changes. That's fine for things like night lights or automatic lamps, but not great if you're trying to capture rapid flashes or high-speed light signals. Characteristics of LDRs. Let's go over some key traits of LDRs so you really get a feel for how they behave. High resistance in darkness, over 1 mega ohm, sometimes even more. Low resistance in bright light can drop to a few hundred ohms. Non-linear response, meaning the resistance doesn't drop in a straight line with light, it curves. Slow response time, ranging from 10 milliseconds to a couple of seconds. Inexpensive and durable, which is why they're popular in DIY projects and mass-market electronics. But keep this in mind. LDRs are not precision sensors. They're great for detecting the presence or absence of light. But if you want to measure the exact brightness level, there are better tools for the job. LDR versus other light sensors. Now, LDRs aren't the only players in the game. Let's quickly compare them to a few other common light sensors. Photodiodes. These are much faster and more sensitive. They're great for digital sensing and optical communications, but they need amplifiers and a bit more circuitry. Phototransistors. Think of these as photodiodes with built-in amplification. More complex, but better for detecting small light changes. Digital light sensors like the TSL2561, these give precise lux readings and communicate over I2C, perfect for smart devices and accurate ambient light sensing. LDRs, simple, cheap, easy to use, but slow and not super precise. So if you just want to know, hey, is it light or dark out? Go with an LDR. But if you need real-time tracking or accurate brightness levels, you might want to look into the other options. How to use an LDR in a circuit. Okay, let's talk practical. How do you actually use an LDR in a circuit? The most common setup is the voltage divider. It's simple and super effective. Here's how you do it. Connect the LDR in series with a fixed resistor. Connect one end to a voltage source, usually 5 volts or 3.3 volts. The junction between the LDR and the resistor becomes your output voltage. That output voltage changes depending on how much light is hitting the LDR. Feed this voltage into an analog input on an Arduino, Raspberry Pi, or ESP32, and boom, you're sensing light. This setup is used in all sorts of projects: auto-adjusting LEDs, smart night lights, light-based alarms, data loggers for environmental monitoring, and yes, it's a go-to beginner project for anyone diving into Arduino or microcontroller electronics. Real-world applications of LDRs. You've probably encountered LDRs dozens of times without realizing it. Here are some places they show up. Automatic streetlights. Detect ambient light and switch on at night. Solar garden lights. Same deal. Turn on when it gets dark. Camera light meters. Help adjust exposure settings. Smartphones. Auto brightness sensors. Computer displays. Dim the screen based on surrounding light. Security systems. Detect if someone passes by and blocks light. Smart home systems. Optimize lighting for energy savings. They're like silent guardians, responding to light conditions and making smart decisions without any input from us. Limitations of LDRs. Now, no component is perfect. LDRs do have some limitations. Slow response time, not suitable for fast or pulsed light detection. Inaccuracy, good for detection, not precise measurement. Environmental concerns. Some LDRs use cadmium, which is toxic, and therefore restricted in some countries due to RoHS regulations. But for learning, prototyping, or basic automation, they're still incredibly useful. So there you have it. The humble LDR, or light-dependent resistor. A simple component with a powerful purpose, sensing light and helping electronics react to the world around them. Whether you're building a night light, tinkering with Arduino, or just curious how your garden lights know when it's dark, now you know. If you found this breakdown helpful, give this video a thumbs up. Don't forget to subscribe, hit the bell icon, and let us know in the comments, what electronic component should we cover next? Thanks for watching, and as always, stay curious.